All right. So we did several examples of evaluating indefinite integrals using the U-substitution technique or the substitution rule. And what we want to do now is look at how the rule works when we're dealing with definite integrals. There's a couple of approaches you can take here, but I'm going to use this one the book presents. When you have an integral, a definite integral from a to b of a function of this form, remember this is like the result of the chain rule, which is where we're getting our U-substitution technique from. Once we transform this thing from x's into u's, what we're doing is we're changing the variable of the function that we're integrating. And it's important to remember that the limits of integration are interpreted as x values. This is x equals a, and that's x equals b. But once we get to this integral over here, we aren't dealing with x's anymore. We're dealing with u's, which are something entirely different. The limits of integration then can no longer be x values. They have to be u values. So how do we find those u values? Well, remember, we define u as a function of x. So if x equals a, the corresponding value of u would be g of a. We plug the a into this function that the u is defined to be. Same thing with my upper limit of integration. So the limits of integration will change along with the integrand. Let's do a couple of examples where we have to do that. We want to evaluate the integral from 0 to 1 of e to the x over 1 plus e to the 2x. This is kind of similar to an example that we saw in the previous video. I'm going to rewrite this as e to the x over 1 plus e to the x squared dx, creating an inside function, something that gives me a clear choice of what u should be. U I'm going to set equal to e to the x, so that du is also e to the x, but with a dx attached to it. Okay? Now, let's change these into u's. Okay? My new integrand is going to look like, here's an e to the x dx, which is du, so I end up with a du there, over 1 plus e to the x squared. The e to the x here becomes u, so I have 1 plus u squared. It's another integrand whose antiderivative will end up being the arctangent function. Arctan shows up a lot in integration. However, there's more to do because, again, we need to change our limits of integration here. The 0 here has to be plugged into this function to give me a corresponding value for u. E to the 0 is equal to 1, so that becomes a 1. And then this 1, the upper limit of integration gets plugged in. E to the 1 equals u, so that's just e, okay? This we know is equal to the arctangent of u evaluated from 1 to e. Now here's the nice thing about dealing with definite integrals and using this technique. When I was doing indefinite integrals, we had to change the u back into a function of x. So I would be changing this u back into e to the x. But I don't actually need to do that anymore because I've accounted for my change of variables by adjusting my limits of integration along with it. So I can actually evaluate this with the u instead of changing things back into x's. This becomes arctangent of e minus arctangent of 1. Arctan of 1 is equal to pi over 4. Arctangent of e, who knows? That's not something that comes out nicely, so I could either plug it into a calculator and approximate, or just leave it alone. I'm going to say arctangent of e, just leave it alone, minus pi over 4. I'm going to leave it in that form. Okay? So that's one example with a definite integral where U-substitution is needed. Here's another example, somewhat of a tricky one, but not too bad. Once again, we have a function that would require U-substitution. There's an inside function here, u equals 1 plus 2x. Okay? Which means du would equal 2 dx. Okay? Now, I don't have a 2 outside of this 2, so I am going to have to manipulate that. I'm going to say this is 1/2 du equals dx. So at some point I can replace this dx with a 1/2 du. I have the square root of u appearing in my denominator, but this x up here is unaccounted for. And remember, we had a way of dealing with that. So what I'm going to do is solve this for x. This would be equal to 1/2 times u minus 1. That's equal to x. Okay? Which gives me something to replace that x with. So now my integral becomes this. The integral of my new numerator is going to look like 1/2 u minus 1 over the square root of u. Let's call that u to the 1/2 power. And then my dx, remember I can replace that with a 1/2 du. So I'm going to bring a 1/2 out du like that. And then I'm going to do some simplifying. I can bring this 1/2 out as well, which becomes 1/4 times the integral of, and then this u minus 1 over the u to the 1/2 power, I can simplify that. U over u to the 1/2 is equal to u to the 1/2. 1 over u to the 1/2 is equal to u to the negative 1/2 du. Now, one thing I have not done in either of these cases, I haven't dealt with my limits of integration. So let me go back a step and do that. If I plug 0 into my expression here, I'm going to get 1. So this 0 becomes 1 as my new lower limit of integration. If I plug a 4, my upper limit of integration, into this expression here, 1 plus 2 times 4 is 9. So my upper limit becomes 9. Okay? Remember, you have to change those. Now I can integrate. This becomes 1/4 times. This is going to become 2/3 times u to the 3/2. Minus, this will become 2u to the 1/2. And we're evaluating from 1 to 9 here. Okay? 1/4 times. All right, so 2/3. What is 9 to the 3/2 power? That's the square root of 9, which is 3, cubed, which is 27. So this becomes 27 divided by 3, which is 9, times 2 is 18. I'm going to get an 18 there. And then here, minus 2 times 9 to the 1/2 power. That's 2 times 3, which is 6. Okay? Minus, plug a 1 in. If I plug a 1 into either one of these, I'm just going to get 2/3 here and 2 there. Okay? Which is equal to 1/4 times, let's see, this is -8, is 18 minus 6, which is 12. And then I have a negative 2, which is going to be like plus 2. 12 plus 2 is 14. So that's going to be 14 minus 2/3. Okay, 14 minus 2/3. Let's get a common denominator of 1/4. What would this be? That would be 42/3. 42/3 minus 2/3. Okay? 42/3 minus 2/3 would be 40/3, times 1/4 would be 10/3. That's my final answer there. Okay? So that's the idea. So one last thing we want to talk about is symmetry. When you are integrating a function from -a to a, so in other words, when the limits of integration are opposites of each other, then what you're doing is you're integrating over an interval that's symmetric about 0. And when the function f of x has a certain kind of symmetry here, there is a shortcut that we can use. If the function is even or if the function is odd, we can abuse that symmetry to make the integral much easier to evaluate. So let's state this theorem. We're gonna look at it from a graphical perspective and then do a couple of examples. If f is an even function, which remember means that f of negative x is equal to f of x for all x on the interval that we're talking about, -a to a, for example, then the integral from -a to a of f of x dx is twice the integral from 0 to a of f of x dx. If f is an odd function, which remember means if f of negative x is equal to negative f of x for all x in our interval, then this integral always comes out to 0. which is the best possible case. You don't have to evaluate anything. It's just automatically 0. Okay, let's walk through this proof really quick and then do a couple of examples. So in the first case, well, actually, let's just say that we have an integral from negative a to a of f of x dx. We can split that into these two integrals, the integral from negative a to 0 of f of x dx and the integral from 0 to a of f of x dx, and then add those, okay? And then what I can do is switch the order of the integration here by putting a negative out front. My printer had some issues here, but that's a negative, not an equal sign, okay? So I have negative this integral plus this integral. Now, if f of x has the symmetry that we're talking about, in either kind of symmetry, we substitute a negative x in for x. So that's suggesting a U-substitution, u equals negative x, in which case du would equal negative dx. And then changing my limits of integration, if I plug a or negative a in for x here, it comes out to positive a. So making a change of variables in this, this integral right here, that x becomes negative u. Then I have a negative du that gets plugged in for dx, but that negative and that negative end up canceling each other. And then my negative a here becomes a positive a, and my 0 would remain a 0 because negative 0 is still 0. So this integral becomes the integral from 0 to a of f of negative u du. Okay, so this is what we end up having. Now, if f is an even function, then f of negative u is the same thing as f of u. So this f of negative u here becomes f of u. And we end up with f of u, or the integral from 0 to a of f of u du, plus the integral from 0 to a of f of x dx. And if you recall, the only difference between these two integrands here is the label that we're using on our variable. U's here and x's here. And we said before that these will come out to be the same thing because the labels are just labels. So we're adding the same integral twice, which is where the 2 is coming from. If we have an odd function instead, then this negative gets brought out of the integral completely, and now I have negative this integral plus this integral, and they cancel each other. That's where the 0 comes from. Okay? Graphically, it's not too hard to see where this is coming from. If I have an even function that I'm integrating over the interval negative a to a, then we have symmetry, even symmetry, which is symmetry about the y-axis. The area under the curve from negative a to a, in this picture, you can see pretty clearly is twice the area just going from 0 to a. So that's what that first part of that theorem is saying. If f is odd, then we have symmetry about the origin, which this graph is one example of that. In a case of symmetry about the origin, in this case anyways, you can see that part of my graph is going to be below the x-axis, so it's counted as negative area. And then the other part over here is above the x-axis, is considered positive. And the symmetry here suggests that these two areas are equal to each other, but when one is counted as negative, one is counted as positive, those cancel each other out and give me 0. Okay? So let's do a couple of examples. I would like to evaluate the sine, the integral from negative 2 to 2 of sine of x cubed over x squared. The fact that I'm going from a negative 2 to a positive 2 is what allows me to start thinking about this symmetry. We need to have limits of integration that are opposites of each other. Now, if I set f of x equal to sine of x cubed over x squared, then what does f of negative x look like? Well, that would be sine of negative x cubed over negative x squared. But negative x cubed is just this, literally negative x cubed. And negative x quantity squared is the same thing as x squared. Finally, the sine function is an odd function, so negatives can be brought out of the sine, and it gives me this, which is the opposite of the function I started with. That's equal to negative f of x. So this is an odd function, which tells me that this integral from negative 2 to 2 of sine of x cubed over x squared dx is just 0, because that's what happens with odd functions that are integrated over an interval that's symmetric about 0. Last example, this guy. f of x, if I set that equal to the cosine of 2x function, then what can I say about f of negative x? Well, that would equal cosine of 2 times negative x, which is equal to cosine of negative 2x, but cosine is an even function, so this would be the same thing as cosine of just 2x. Being an even function, I can rewrite this as 2 times the integral from 0 to pi over 3 cosine of 2x dx. Now, how do I integrate this? Well, I actually need a u substitution here as well. I would have to set u equal to 2x. Okay? du would then be 2 dx. Yeah. Okay? Now, this 2, I can use this 2 and bring it in to count as this 2 right here. So I have a 2 dx already appearing. Those together are going to give me my du. Then I have cosine of u left in there. Plug a 0 in here. U equals 2 times 0, which is still 0. Plug a pi over 3 in here, and I get 2 pi over 3. Okay? This, when I integrate, is a really simple one. I get sine of u from 0 to 2 pi over 3, which is equal to sine of 2 pi over 3 minus sine of 0, which is equal to sine of 2 pi over 3 is root 3 over 2 minus 0, which is just root 3 over 2. The benefit of this technique is it's a lot easier to work with zeros than it is other numbers most of the time. And so I gave myself one of my limits of integration, I changed one of my limits of integration into an easier one to manage. Okay, that's going to wrap up section 5.5 and the class.